made sense. I will post them somewhere afterward.
Okay, no, you can just send it to me. I'll post it on the website. But
okay.
I will start in a minute. I see you're trying to get it real quick.
Yeah, it might not be worth it.
Sometimes doing these things last minute doesn't work so well.
Yeah.
I've been getting ready for a talk and my computer decides that it needs to, totally reinstall everything.
Yes.
When I tweak, play around with it. Okay, maybe we'll get started. So welcome everyone to One World Probability Seminar. Before we get started, just the general rules of the game. So I'm going to turn off the ability for people to unmute themselves right now. So if you have questions, just put them in the chat and either people will respond to them there or we'll raise it to the attention of the speakers. At the end of this first and second sessions, we will unmute everyone or allow everyone to unmute themselves and we can all join together in applause. It's a pleasure to have two speakers today. The first who I'll be chairing is Levine, and he'll be speaking to us about abelian sand piles and abelian networks. So Lionel, why don't you take it away?
Okay, thank you, Ivan and Milton. It's a pleasure to speak here, and I just wanted to say, like, one of the few advantages of this pandemic is bringing together researchers from all over the world who wouldn't normally necessarily meet each other at conferences and so on. So let's take advantage of that and interact more. I want to tell you today about a topic I've been working on for a long time, ever since my PhD, and it keeps leading in new and interesting and unpredictable directions, and so I keep going on it. First, I'll tell you about the abelian sand pile model, which is a very simple particle system with very interesting and in some cases still not well understood behavior. And I'll tell you some things we like about that model and some things we don't like. It has certain non-universal features. And because of those, we're going to be after a model which corrects that non-universality. And we're still searching for the right universal version of the model. But I will kind of guide you through the search space of abelian networks, which is this big phase space of many different types of particle system. And I'll point out a particular point in that phase space called activated random walk, which is, I would say, currently the most promising candidate for the universal model we're looking for. And in the second hour, Levine and Rolla will tell us a lot more about that particular model, activated random walk. But first, the abelian sand pile. So this is a toy model of sand sprinkling. You sprinkle sand on top of a pile, and when you drop a sand grain on the pile, it might just stay there, but it might dislodge sand grains nearby. And when they start to topple down the pile, they might dislodge other sand grains. And so sometimes you get avalanches of sand trickling down the pile. Now what you find, and they've done experiments with real sand and with other media, like they did a giant experiment with rice, where there's a critical slope for such piles, which I call zeta C. And this slope depends on some of the details of the physical situation. So it depends on the shape of the sand grains. It will be different for sand and for rice. It depends on things like temperature and humidity, okay? But once you fix those kind of background parameters, there's one critical slope. And at that critical slope, what you see is that the probability distribution of avalanche sizes, when you drop a single grain on top of the pile and ask how many grains are dislodged, follows a power law. if you started at a different slope, you would not see this power law. And there are sort of two cases of that. You could be above the critical slope. So that's this picture here at the bottom left. So zeta is bigger than zeta c. So you have a very steep sand pile. And here it's very unstable because it's so steep. And so when you drop just one sand grain on top of the pile, it is likely to cause a giant avalanche, which substantially flattens the pile out. The other case is that you're subcritical. So you're starting with a flat sand pile that's below the critical slope. And here, when you drop a sand grain, you're likely to see not very much happening. So it's very stable. It's very hard to observe. It's very unlikely to observe big avalanches. And because of that, when you drop sand on one of these flat sand piles, it tends to get steeper over time as sand accumulates at the top. And this creates a kind of natural driving toward the critical point. So even if you started with a sand pile that was far from the critical slope, if you just sprinkle enough sand on top of it, it will tend towards the critical slope. And this motivated three physicists, Bach, Tang, and Wiesenfeld in 1987 to propose this idea that they called self-organized criticality. And their idea was, in most mathematical models, you only see power laws and long-range correlations at one particular value of a parameter. And given that you only see them at one value, you might expect them to be rare in nature. But if you go around and look at many systems in nature, not just sand piles, but if you look at distributions of earthquake sizes or wildfires or epidemics, financial crises, and so on, power laws are everywhere. Long-range correlations are everywhere. And so we need some mechanism that explains why they're not rare. And their idea was that such systems must have some dynamics that drives them toward criticality, even if they start far away from criticality. Okay, and so they proposed this model as a kind of a toy model of the phenomenon, but one that could hopefully teach us something about it. So let me tell you the toy model. This will make sense on any connected. Here I wrote finite graph. These are notes from a course I'm teaching. But for this talk, I'm going to be interested in infinite graphs too. So I'll put locally here. It can be a locally finite graph. In particular, I will focus a lot on the square grid graph, Z2. Okay, and we'll write tilde for the adjacency relation in this graph. And then we define a sand pile on the graph to be an integer valued function on the vertices. So here's how you should think of this function. If you have a vertex I, S of I, if it's a positive number, it represents how many grains of sand are located at vertex I. I may call the grains of sand particles or chips because it takes fewer syllables to say. And we also may sometimes want to allow negative values of this function S. And that you should think of as not a particle, but a hole located at vertex I that particles can fall into. And in this toy universe, there's one law of physics, and it's this one down here. It tells us when a vertex can topple. And you could topple if the number of chips at that vertex is at least as large as the degree of the vertex, which is the number of neighbors. So in Z2, if you want to focus on the particular example of Z2, you won't lose a lot for this talk. And there the degree is 4. Okay? So the magic number for Z2, every vertex has 4 neighbors. So if you have 1, 2, or 3 chips, you cannot topple. But if you have 4 or more chips, you could topple. And what does toppling mean? It means sending one chip to each neighbor. So a toppling in Z2 might look like this. So maybe I have it on the next slide. Okay. So toppling in Z2, you have 4 chips somewhere, and one of them goes to each of the 4 nearest neighbors. Okay, so just to set notation, we can describe topplings in terms of the graph Laplacian. So I want to think of, you could think of the Laplacian as a matrix, but I want to think of it as, I want to use the fact that it's an integer matrix. So I'm going to think of it as acting on the space of integer valued functions on the vertices, z to the v. Okay, so that space has a standard basis, delta I, which is 1 at vertex I and 0 everywhere else. And then delta is the linear operator on that space. So it takes integer valued functions to integer valued functions. And here's the formula for it. So it's the value of the Laplacian of f at vertex I is the sum over neighbors of the differences fj minus f of I. And one way to write this to see its relevance to the sandpile model is you can take out the minus f of I term, and it occurs degree of I times. And then if you think of f as a function counting how many times did each vertex topple, then delta f counts the net change in chips. So this part will, every time a neighbor j of I topples, it sends 1 chip to I. And so the total number of chips received by vertex I is this sum. And every time I topples, it emits degree of I chips. And so the total number of chips emitted by I is this. And so this difference is the net change in chips. Another way to see the relevance is just take the special case when f is the basis function, that's 1 at I. Then when you take its Laplacian, you'll get the function which is 1 at each neighbor of I and negative degree of I at I. So toppling vertex I transforms a sandpile S to the sandpile S plus the Laplacian of delta I. There's a lot I want to cover, but I don't want to rush. So you should please stop me with questions in the chat if anything is unclear. Also, I feel like I'm speaking into a black box with everyone's video off. So if you can turn your video on, I would love that. Thank you. All right. Something you might wonder about this toppling rule is when to apply it. So I might have a sandpile which is unstable in many different places. So there might be many different vertices which are ready to topple. And then I have a choice of which one to do first. Okay? So one of the beautiful things about this model is that those choices don't matter. So let me spell out what it means not to matter. So let's suppose we have a sandpile S, or let's call it S0, and then I topple a vertex x1, and I arrive at a new sandpile, which is the original one plus Laplacian of delta x1. Then I could topple another vertex x2 and arrive at a new sandpile s2, and so on. Okay. So let's suppose I'm looking at this sandpile, and I'm kind of playing God in this universe. So I'm choosing, okay, I want you to topple now. All right, now it's your turn to topple. Okay, now you can topple again. I'm choosing the order in which things topple. So I'm choosing a sequence of vertices to topple. And let me define that sequence to be legal if all those topplings were actually allowed in the model. So what does it mean to be allowed? It means that when it comes time to topple the ith vertex in the sequence, I look at my sandpile at time I minus 1, and I just check to make sure, does it have at least a degree of xi number of chips, so that toppling is allowed. Okay, so that's a legal sequence of topplings. And the best kind of sequences are the ones which stabilize the sandpile. So I'll call a toppling sequence stabilizing if after I perform all the topplings in that order, the resulting sand pile is stable. It can't do any more toppling. And what does it mean to be stable? It means every vertex has fewer chips than its degree. Okay, so for any given sand pile, there might be many choices of legal stabilizing toppling sequence. And I would like to formalize the idea that order doesn't matter. So, good question in the chat. Is the model in continuous time? Right. So currently I'm talking about discrete time toppling procedures where you topple one vertex at a time. You could, however, run this model in continuous time, for example, by giving each vertex a Poisson clock and saying, when your clock rings, check if you're allowed to topple and topple if you can. And by the lemma that I'm about to state, those two descriptions of the model will result in the same final state. So one thing to be careful about before we state this lemma about order not mattering is that there is a basic dichotomy in this model. Some stand piles stabilize and others explode. Right. So here's an example of a little graph with 4 vertices and 5 edges. And this sand pile has, 2 chips in the upper left, 4 chips in the upper right, 0 chips in the lower left, -1 chip in the lower right. And there are 2 unstable vertices, the top 2. So I could topple them in either order. And this little diagram shows whichever order I choose, I arrive at the same stable sand pile in the end. In this case, we say that this particular sand pile stabilizes because there's a finite sequence or locally finite sequence of topplings that results in a stable configuration. But here's a configuration that doesn't stabilize, this one down here. It has the same total number of chips as the one at the top, has 5 chips. But if you topple this upper left vertex, then now this upper right one becomes unstable, and then this lower left becomes unstable, and then this lower right and upper left become unstable. And if you choose to topple the lower right, you'll get back to the same configuration you started with. Okay? And so you could continue this cycle infinitely. So we say, in this case, we say that the sand pile explodes. Okay, so here's the formalization of the statement that order doesn't matter. It goes by the name abelian property, but what we'll see in the proof is we could prove something a little bit stronger than the claim that order doesn't matter, and that stronger claim goes by the name least action principle. Okay, so here it is. So suppose I give you a sand pile to function on the vertices of our graph, and suppose that there exists a stabilizing sequence for this sand pile. Then any legal sequence is a subsequence of a permutation of that stabilizing sequence. So just the existence of one stabilizing sequence without any worrying about whether the topplings in that sequence were legal or not implies that all the legal sequences are shorter than that sequence Y. And in fact, not only shorter, they are subsequences of permutations of Y. So just from the existence of this Y, what we get is that there exists a sequence that is both legal and stabilizing. And furthermore, any 2 such sequences must be permutations of each other. Okay, and Leo asked, I don't usually do this proof in talks, but Leo asked me to do it. So really what it will come down to is a monotonicity property of the Laplacian. So what we'll do is we'll induct on the length of this sequence. And suppose X is a legal, so we're going to prove part 1. So suppose X is a legal toppling sequence, we want to show that it's a subsequence or permutation of this y. Well, x being legal means we can certainly topple the first vertex x1. So sx1 better be bigger than the degree of x1. Okay, but y was stabilizing. And so if you take the final stable sandpile that comes out of y, x1 better be stable in that configuration. Okay, so this number must be strictly less than the degree of x1. And the only way for the number of chips at x1 to go down is if x1 itself topples. This is the monotonicity. So if you topple any other vertex, well, it might not give any sand to x1, or it might give sand to x1, but it can never take sand away from x1. So the only way to decrease the number of chips at x1 is actually to topple x1. And so I hope you could see the very bottom of the slide. Sometimes there's an issue with that. So what follows is that yi equals x1 for some I. So this x1, the first term of our legal sequence, it must occur somewhere in this y sequence. So we're going to take that and induct. So now this shortened sequence x2 through xl is legal, and this shortened y sequence where we remove one of the terms equal to x1 is stabilizing. Not for the original s, but for s plus delta delta x1. And so now you apply the inductive hypothesis to this situation. And doing this, you get to the trivial base case that the legal sequence was empty. Okay, so that was kind of quick, but not much goes into it. It's just this observation that you cannot lose chips at x1 except by toppling x1 itself. Okay, and now to prove the rest of the lemma, we want to show that just from existence of a stabilizing sequence, any legal sequence must be finite. Well, certainly there exists a legal sequence, the empty sequence, and all the legal sequences by part one, they have length at most the length of y. Okay. So let's take a legal sequence of maximal length. Then such a legal sequence must also be stabilizing. Otherwise, you could do another toppling and append it. So that tells you that there is a legal stabilizing sequence. And if you have two such sequences, then, well, they're each subsequences of permutations of one another, and so they must just be permutations of one another. So the upshot is that choices of what to do when don't affect the final state of the sandpile, and they also don't affect what we call the odometer. So that's the function u, which is defined as the number of occurrences of x in any legal stabilizing toppling sequence. So this number doesn't depend on the choice of legal stabilizing toppling sequence. And so we can define the stabilization as the sandpile we get from performing the topplings in any legal and stabilizing toppling sequence x. And one compact way to relate these objects is this equation at the bottom. So the stabilization is obtained from the original sandpile by adding Laplacian of the odometer function. Okay, and this brings me to the least action principle I mentioned. So we've been so far approximating this odometer function from below by performing legal topplings, but we could instead try to approximate it from above. And the way you would do that is just observe that this final stable sandpile S hat, well, by definition, it must be pointwise smaller than degree minus 1. So suppose I'm given any function, let's call it w, with the property that when I take my sand pile S, add Laplacian of W, that I get something pointwise smaller than or equal to degree minus 1. If there exists such a W, then S must stabilize, and the odometer of S, the number of topplings that occur, is the pointwise infimum of all such functions. So it's the infimum of all W satisfying. W should be non-negative integer valued and satisfy this Laplacian constraint. So this is called the least action principle, and it falls out of the lemma that I just proved for you. And one way to kind of gloss what it's saying is sand piles are lazy, or if you prefer more positive sounding words, sand piles are efficient. So what do I mean by that? I mean, each vertex in your graph, it doesn't want to do more work than it has to do to stabilize the sand pile. So we're going to take this large family of functions, all the functions that would do the amount of work required. W does the amount of work required to stabilize the sand pile. So think of W in this family as a recipe for how many times to topple each vertex. And the recipe succeeds if when you do those topplings, you get something pointwise smaller than degree minus 1. And the pointwise infimum of this family is actually the odometer function. So each vertex is doing the minimum amount of work required to stabilize the system. Okay, now that we have this toy universe of the abelian sand pile, we could do some experiments in it. And let me focus on two very natural experiments. They'll both be on the square lattice. One will be starting n chips at the origin. Right? So this is most similar to the motivating example of a big pile of sand. You sprinkle a lot of sand at the origin. And by this abelian property, we could think of dropping the sand grains one at a time, and each time you drop a sand grain, you do all the topplings needed to stabilize it, and then you drop the next sand grain. But we don't have to do that. We could also just put all the sand grains at the origin, and then just do all the topplings at once. That will give the same final configuration. And I don't have a picture for you, but this configuration has a lot of intricate fractal structure in it. So it's a very complex thing. What I want to stress about it is that it has a limit shape. So Pegden and Smart proved existence of this limit, which appears to be lattice dependent. So if you did this on the triangular lattice instead of Z2, you would get some other shape. Both of the shapes have internal structure, and the internal structure is, the fine details of the internal structure really depend on the lattice. There is one case, namely the square grid Z2, where although we don't have an exact characterization of what this shape is, we do have a limiting version of the least action principle. So we can describe the odometer as the pointwise smallest, the scaling limit of the odometer as the pointwise smallest function satisfying a certain condition. And you can see in that condition where the lattice dependency comes in. So there's a certain set of 2x2 symmetric matrices which give a constraint on this scaling limit of the odometer. And that set of matrices depends on the lattice. For the particular case of Z2, we have an exact description of what that set of matrices is. That's a long, beautiful story, which I won't tell you today. The point I just want to emphasize for today is the lattice dependence. Now, that lattice dependence, interestingly, goes away if you tweak the model slightly to what we call the divisible sand pile. And the only difference with divisible sand pile is allowing our odometer to be real valued instead of integer valued. So if you think about what that's saying, it's allowing for fractional topplings. So instead of these indivisible chips, which you have to wait for 4 chips in Z2, and then you send 1 to each neighbor. If you had only 2 chips, well, that's okay. You could send 1/2 of a chip to each neighbor. You could still send them equally. So in the divisible sandpile, so the law of physics in this divisible sandpile is each site, it keeps mass 1 for itself, but anything excess of 1, it sends equally to its neighbors. And for that model, it's not hard to show that the limit shape is a disk and that there's no internal structure. So you get a set of sites. If you started mass n at the origin and spread them out according to these fractional topplings in Z2, then you'll get a set of sites that fill up completely, and you'll get some sites on the boundary that fill up only partially. And the set of sites that fill up completely is asymptotically a Euclidean disk. Okay, so that's kind of surprising at first sight, that just this change of integer topplings, changing them to fractional topplings, has a giant effect on the scaling limit. So this is one kind of symptom of non-universality in the abelian sandpile, which is the lattice dependence. You can see it also if you do a completely different experiment. Namely, instead of starting with a finite number of chips all at the origin, let's start with an infinite number of chips spread randomly throughout Z2. So it could be any stationary ergodic configuration of chips on Z2. If you like, it can be IID. So there's an independent random number of sand grains starting at each site of Z2. Oops. In that case, you can ask, does the sandpile stabilize? So to focus on just one family of IID sandpiles, you could take Poisson marginals. So you take a Poisson number of chips with mean zeta independently at each site of Z2. And then there's this dichotomy, right? Either this infinite sandpile will stabilize almost surely or explode almost surely. And there's some critical mean where you switch from stabilizing to exploding. But what you find is that this critical mean depends on the distribution. So for Poisson, the critical mean turns out to be about 2.125288 for Poisson. But if you took a different distribution, you would find a different critical mean. And there are simple examples showing that the mean can be anywhere, depending on your distribution, it can be anywhere in the interval from 2 to 3. Divisible sandpile, again, has a much simpler and more universal behavior. No matter what your distribution is, there's a single critical mean. So if your mean is less than 1, then you stabilize almost surely. If it's greater than 1, then you explode almost surely. And the case equal to 1 is interesting. You also explode almost surely in that case. That's another interesting story. Okay. There are other experiments you can do in this sandpile universe on finite graphs. So you can restrict to, for example, a finite torus, Z mod LZ squared. And there are 2 Markov chains you can view on this finite graph. Call them the free and wired chains. I'll just describe them in words. So the free chain has as its state space all of the sandpiles on this finite graph. And it's a discrete time Markov chain. And the update rule is add 1 grain of sand at a random vertex and then stabilize if possible. The reason I say if possible is that, as we've seen, some sandpiles explode. And so in particular, in this free chain, you're adding more and more sand, which has no way to escape the finite system. And so at some point, you will reach a sandpile that explodes. And you can ask, when do you reach that point? How much sand does it take to reach that point? And what does this, what I call the threshold state, look like? the state just at the moment when you drop that last grain of sand to create an infinite avalanche. There were some conjectures in the late 90s, which Leo may talk about in the next hour, relating this free chain to the wired chain, which fixes some boundary where sand can exit the system. So for this discrete torus graph, you could pick one vertex, call it the sink, and sand falls off there. So if sand enters the sink, it disappears from the system. The wired chain has the advantage that you will always stabilize, no matter how much sand you start with. So you can run this chain as long as you want, and so it will have a stationary distribution. And there's a beautiful theory of that distribution. So the recurrent states of this wired chain are equal in number to the number of spanning trees of this finite graph. And using bijections between spanning trees and recurrent sand piles, you can prove an infinite volume limit exists for this wired chain stationary distribution. That's a theorem of Threya and Uri. And the hope was in the late 90s that this infinite volume limit would be a kind of universal object, and it would be a way to make predictions about self-organized critical systems in general. And then, what we started to find over the years, the evidence built up of this non-universality, that it's a very picky object. So it's a beautiful thing, but it only describes what I would call very slowly driven systems. So systems that took a long time to reach criticality. Those could be well described by this stationary distribution of the wired chain. But what you find when you compare the free and wired chains is that you can couple them, but the wired chain has a rather slow mixing time. So what we proved with Daniel Jerrison and Bob Huff is that the mixing time of this wired chain is order L squared log L. And this log L is, sometimes a log factor is just some annoying detail, but this log factor really causes, it's important, it causes a lot of problems. The reason it causes problems is that if you want to compare the free and wired chains, well, you can only run the free chain up until the time when it explodes. And that means you only have time L squared, and then you've exploded. So although you can couple these two chains, you have not given the wired chain enough time to fully mix. And that's a kind of underlying cause of a lot of the non-universality that we see in the abelian sand file. So given these shortcomings of the sand file, I want to tell you about how my approach to searching for a more universal model. So my approach is to say, let's try to search in the space of all particle systems that have the same kind of abelian property that the sand file has. So these systems I call abelian networks. And there's a kind of shift in viewpoint that takes place here. So with the particle system, you tend to think of the graph that it's living on as a passive substrate. The graph just sits there and doesn't do anything. It's just a place where your particles live. Your particles are where the action is. Abelian networks was inspired by a paper of Dar from 1999, where it's a survey paper about self-organized critical systems. And there's a paragraph in there where he explains how you could think of this abelian property instead of as a property of a particle system, you could think of it as a property of some computational network. So instead of viewing the vertices of your graph as passive, you view them as little processors. Okay? There's a little computer at each vertex. And you could view the particles in your system as messages that are sent between these processors. So I want to tell you about I won't give you the general definition of an abelian network, but I'm going to tell you about a big subclass of them, the unary networks with two stacks. And this class includes the sandpiles and many other interesting models, including the activated random walks that Levine and Rolla will talk about in the next hour. So here's how it works. Each vertex of our graph will have two stacks of instructions. So it has a movement stack and an activity stack. You could think of these stacks as some quenched randomness that goes into the model. They don't have to be random, but they could be random, and we will be interested in taking them random. So, and here's the rule of physics in this two-stack unary network. So you look at a vertex V, and you say, let's suppose that so far in the evolution, it received a total of L letters. Letters are my rebranding of particles. So I'm going to call the particles letters. And well, one reason for changing the name is that particles are conserved, but I don't want to insist that letters be conserved. Okay, so if V receives a total of L letters, then V sends a total of alpha LV letters. So that's this alpha coming from the activity stack. So that's how many letters it sends. And where does it send them? That's governed by the movement stacks. So the kth letter is sent to the neighbor row K of V. Okay. So you think of the movement stacks as it's a list of vertices that tell you where the particles are going. The kth particle sent from vertex V is sent to row K of V. The activity stacks tell you when it's allowed for particles or letters to be sent. Namely, it's allowed if you've received a total of L letters, then the number you're allowed to send is alpha LV. And there's only one assumption that we're going to make about these stacks, which is that the alpha sequence is increasing. So that's going to be crucial. So the number of letters you're allowed to send is increasing as a function of L, the number of letters you've received. Okay, so what I want to do with the remaining 10 minutes or so is just show you how to recast a lot of familiar and a few unfamiliar particle systems in this framework of unary networks with two stacks. Okay, so familiar examples. Let me start with the most familiar, simple random walk. Okay, so instead of my particle being the one doing the action, it's the vertices that have to do the action, right? So the particle is just a passive message that gets sent between these vertices, which are processing the message. Okay, so we're going to take the activity stack to be just the identity function, alpha L equals L. So that means if you've received L particles, then you get to send out L particles. That just means the walker can't stop anywhere. If it arrives at vertex V, then that's a new particle received by V, and so V is supposed to send out a new particle. And for simple random walk, well, we take the movement stacks to be IID uniform on the neighbors. Okay, random walk with killing. So same as above, except if you want to kill your walk, say at some trap vertex Z, just set activity stack to be 0 for all L. So that way, Z is never allowed to send out any particles at all. Okay, branching random walk, same movement stacks, but you could take your activity stacks instead of deterministic like above, you could take them to be random. So take them to be, say, a sum of independent natural number valued random variables, right, which tell you, so the random variable NL of V is telling you how many offspring you should have. The nth time a particle arrives at V, there will be an offspring event, right? So you sample independently from whatever your offspring distribution is, and that's how many particles you're allowed to send out. A very important example is internal DLA. And so this is the model where your particles do simple random walks. However, the sites are sticky. So each site can attract one particle and make it stay there. So, in the example, when you start n particles at the origin, for example, this is often described as, you do a simple random walk until you reach an unoccupied site, and then you stay at that unoccupied site. Then you start a new particle at the origin, simple random walk until you reach an unoccupied site. So this is accomplished by just setting the activity stack to be L-1 instead of L. So if you've received a total of L particles, then you will send out L-1, which you'll keep 1 for yourself. Okay, abelian sandpile. So that's the model we spent the first half hour on. These stacks are deterministic. So what you do is you take your movement stacks to be periodic. So you take a cyclic permutation of the neighbors of V, and you just cycle through your neighbors in that order. And you take the activity stack to be this expression, which just comes out to you round down the number L to the closest multiple of the degree of V. So what this is saying is, if you've received L particles, then you can send out almost L particles, but you need to wait until you receive a multiple of the degree of V until you send out the next batch. And because we take the movement stacks periodic, that accomplishes that when you send them out, you send 1 to each neighbor. Looking at these two examples, the sandpile and the simple random walk, you might ask what happens if you kind of make a hybrid of them. So you take the periodic stacks for movement, like in the sandpile, but you take the alpha L equals L, like for the simple random walk. And that gives a very interesting model, which I don't have time to say anything about, but it's called rotor walk. And it's a kind of de-randomization of random walk. Okay, and one can kind of interpolate between random walks and rotor walks to get something which you might call random walk with local memory. So here you keep this alpha L equals L condition, but you take your movement stacks Markovian. So this would be saying each vertex retains some memory of what it did in the past. And then when your walker arrives at a vertex, it will jump to a random neighbor whose distribution is some function of that memory. There's many interesting walks in this class. Okay, and now for my last 3 examples, these are going to be heading towards the candidate for a more universal model of self-organized criticality. So one is called the stochastic sandpile. And the idea is that, this sandpile was problematic because of slow mixing. And one reason for the slow mixing is that there's not much randomness in the sandpile model, right? We saw that the stacks are all deterministic. So the only randomness was in the random locations where we were dropping sand on the pile. So let's add more randomness to it in the hopes that that will make it mix more quickly. We could do that by taking an activity stack, which is, let's say, alternates between L and L-1. So it's L for L even, and it's L-1 for L odd. And then we take movement stacks to be IID uniform on the neighbors. So what this does is it says, every time you receive a pair of particles, you can topple them, but you topple them to independent random neighbors. So your topplings are stochastic instead of deterministic. It's a very natural model, but seems very hard to prove anything about. So almost all the interesting questions about stochastic sandpile are open. you could try the opposite approach, which is instead of taking the movement stacks random and the activity stacks deterministic, you could go the other way. So let's take the activity stacks to be periodic, but the movement stacks to be periodic, but the activity stacks to be random. So let's set alpha L to be either L or L minus 1 independently for each L and with some probability P of being L. So what this is saying is, this model is called the Oslo rice pile. It's supposed to model a pile where the grains are kind of elongated in shape. So sand grains are approximately spherical, but rice grains, of course, are long. And the effect of that is somehow that when a rice grain trickles down the pile, the orientation at which it lands affects how easy or hard it is to perturb it in the future. And that's kind of modeled here by this random threshold alpha L. So what this alpha L is saying is that every time you do a toppling, you resample the threshold. So sometimes the threshold is 1 and sometimes it's 2. So if the threshold is 1, then your particle has to keep going. If the threshold is 2, it can stay there until another particle jumps on top of it, and then they both, then you do a toppling. Okay, and having seen these two examples, it's natural to go all the way and take both stacks random. And so that's when we arrive at the model that's the topic of Leo's talk, activated random walk. And so in this case, both stacks are IID. So you take the movement stacks to be IID and the activity stacks to be IID. And so I'll let Leo describe what the equivalent particle system is. You can describe this in terms of walkers that fall asleep and then get woken up when other walkers jump on top of them. But it often seems from that description of the model, like, why would you choose to study this particular model? And I think this viewpoint, viewing these models as abelian networks, kind of indicates why activated random walk is a really natural model, because it is essentially the only abelian network that has both of its stacks IID. So there's this one parameter family of models. Parameter is P, and when you take P equals 0, you get simple random walk. When you take P between 0 and 1, you get activated random walk with sleep rate lambda. And when you take P equals 1, you get internal DLA. These are basically the only models which have both stacks IID. And so stands to reason it's a good place to start in our search for a universal model of self-organized criticality. So I'll end here, and looking forward to Leo continuing the story.
Okay, so I just enabled everyone to unmute themselves. So if you want to, please unmute and join together in applause for Lionel's talk. And so we have time for questions. We'll start Leo's talk a little after 11, but just feel free to shout out a question if you have one.
Ask a question.
Yeah, Takis.
So what is the exact definition of self-organized criticality? Describing the asymptotic behavior or what? Sorry, I just don't know that.
Yeah.
I like your talk was great. Thank you very much.
Thanks for the question. So it's one of these physics buzzwords, right? So if you ask 3 different physicists, you'll get 5 different answers, right? But what it means to me is long-range correlations and power laws. So at least that's what criticality means to me. So the self-organized part of it means some kind of dynamics which will make the critical state a fixed point. So that even if you started your system far away from criticality. When you run the dynamics, it will converge to the critical state.
Mm-hmm. And when you say power laws and what's it, long range correlation, you're talking, for example, in your model on Z2, you're talking about the spatial aspect of the stationary distribution, for instance. It's long range correlation there.
That's right.
Is that what you mean?
Yes, yes. So
What happened?
So there are many ways. So that's one manifestation of long-range correlation, right? So you have this stationary distribution on the recurrent sand piles, and it has a power law decay. If you look at how many sand grains are here versus how many sand grains are here, that decays as the fourth power of the distance in this case. So in particular, that's a pretty fast decay, but it's not exponential. So it's still a long-range correlation. Another manifestation of it would just be, let's say I add a sand grain here and then stabilize. What's the probability that I get a toppling over here? Again, that follows a power law. Another version would be, let's say I add a sand grain here and I look at the total number of topplings that happen. So I get some avalanche, so some random set of sites that toppled. So I could look at the total number of topplings. I could look at the total number of sites that toppled. I could look at the diameter of the sites that toppled and so on. So there's all these different measures of avalanche size, and they're all conjectured to obey power laws. However, to show you how far we are from understanding this model still, there's not even a clear prediction in the physics literature on what the exponents should be for many of these power laws.
So I have a question, probably a very simple question. So in your last display, you have this relation between simple random walks, activated random walks, and internal DLA. So do they hold also for weighted graphs? Because the first one is usually the way on which we construct Markov chains in an elementary course, no? I mean, one possible way to construct a Markov chain is to say, okay, you open the envelope and you go somewhere else, etc., which correspond basically to what you described here. So what happens in weighted graphs, you get also these other two versions of these processes on weighted graphs?
Yes. So if I understand your question right, you want me to generalize from simple random walk to other random walks. And yeah. Yes, so all of these models make sense for a general, you could replace the simple random walk by any Markov chain. And then you can do activated random walk with that underlying Markov chain, and you can do internal DLA with that underlying Markov chain. So yeah, in that sense, there's more than one parameter P, right? Because you can vary the step distribution. So thanks for pointing that out.
Thank you.
Are there other questions? Okay. So if not, I think now is a good time to take maybe a 1 or 2 minute break, and then we'll transition over to Leo. So we'll reconvene in 2 minutes. Okay, so I think Lionel, you probably need to unshare your screen so that
Okay.
there. And I'm going to put the slides for Leo's talk in Dropbox. Hopefully everyone will be able to open that. And we'll post Lionel's slides on the website also a little later.
Okay, Leo, so could you share your screen?
Yeah, so there are three of me in the meeting. I am writing here. I can. The camera is here, but I can see you here, and I can only see very few of you. So yes, it's nice to have some cameras to talk to, some faces to talk to, if you can.
Very good. So, okay, let us then start with the second talk of today. So, which is going to be given by Leonardo Rolla. Your current affiliation, I don't really know.
I'm on leave from Mimas Conicet, and I'm at Warwick.
Very good.
He's one world. He's everything. He covers the whole world.
Trying.
And so he's going to talk about the activated random walks on ZT. So okay, so you probably heard Ivan at the beginning about the rules. I just want to mention that the seminar is also transmitted on YouTube in case you have an unstable connection. Usually YouTube works better because they have this buffering delay that allows to make things smoother for unstable connections. And also you can use it if you missed something that you want to rewind a few minutes. You can check it on quickly on YouTube as well. Okay, so now let me give you Leonardo Rolla, who's going to talk about activated random walks on ZT. So please go
thank
ahead.
you, Milton and Ivan and all the one world probability project for the invitation. It's really a big honor. And apologies to those who have already heard me giving a talk about activated random walk 5 times already. I hope there is something new each time we give a talk about it. And I am not going to assume everyone in the room has followed Lionel's talk completely. That's a big mistake to make, is assume people have been following the previous talk all the way until the end. But I will allow myself to skip all the motivation part. And if you didn't understand the motivation, you will just think the motivation is that this model is cute. So let's just briefly rephrase or say a small bit of the motivation, which is what is called driven dissipative dynamics in this context of self-organized criticality for reaction diffusion systems, would be the following version. This would be what Lionel was calling the wired version. So think this is a table. Okay, it's a funny way to draw a table. This is a table. We are throwing mass on this table, and the mass, it relaxes and reaches some stable configuration according to some mechanism, and the mechanism is there are many candidates for this mechanism, and the one I'm going to talk about today is the activated random walk. And this the narrative would be a system is driven dissipative if the drive is that very slowly we are adding more mass to this table. To this, the tables you can think, of course, is a capital lambda here is just a large subset of some nice graph, ZD, for this talk. So drive means we are adding this mass here and giving it time to handle it. And the dissipation is that when it is killed when it reached the boundary, which Leonel was referring to as maybe there is one big site outside. We are all connected to that site, but that's a very selfish site. particles go there and just stay there. It won't release any particles. Okay, I like to make a mess and erase it from time to time. And if we start from an empty configuration here, and we start from an empty configuration, and we're slowly adding one and more particle little by little, and we count. We keep track of how many particles we have added to this region, and here we count how many particles are still there once this configuration stabilizes. Then, well, of course, this retention will be at most the injection. This is the best we can hope for, is just if you never lose anything through the boundary. And well, it turns out you will lose very little through the boundary for quite a long time. I mean, maybe we are so unlucky that whatever we throw on this table will land close to the boundary and be killed. Or we can also be so unlucky that we throw something on the table and it makes a small disturbance. It disturbs a bit the configuration there, and we end up losing perhaps even more than one particle through the boundary. So this graph here is a graph from natural numbers to natural numbers. It can increase by at most 1, and typically it will increase by 1, and it can also decrease, and it can also stay constant. It stays constant if whatever we add causes one particle to leave. And the description would be that, well, if this lambda is really very large, and we look at this graph from the right scale, then we're losing mass here, which is essentially negligible, the amount of mass we're losing. So essentially we're just going up with a slope 1. There's a 45 degrees angle here, until the system reaches a point where it is saturated. It's saturated, it's not willing to accommodate any more mass. And if it would have more mass inside, it would be very much looking forward to lose it. And if it had less mass, it would be able to accommodate more. So there's a self-balancing mechanism here. And what's interesting is that in this dynamics, you have, let me put quotation marks here for Takes, so we don't have a precise definition of what it means to be a critical state, but it has many of these features that you would like to associate to being critical. And we're interested in describing how it relates to a system without drive, without dissipation. So how do you remove the drive, or just don't add particles to this box anymore? And how do you remove dissipation? Then you need to specify boundary conditions. Well, let's remove boundary conditions altogether by considering an infinite graph that does not have a boundary. And these should be related in many ways, and this is still very poorly understood. What I would like to mention is this conjecture that it increases with slope 1 and then it stays there. This is what you see at the scale of the law of large numbers. And if you want to see this fluctuation here, you need to amplify and see it in order to see something. That's what you see this critical state if you look with the microscope of the configuration. And for the infinite volume conservative system, we have what is called an absorbing state phase transition, which says if we run this dynamics on the infinite volume and the average density or the average number of particles per site is small, whatever mechanism that we are using here, we replicate it in the infinite volume, you get a particle system that will die out. It will fixate, meaning any finite region, we keep looking at it, and eventually we don't see any activity there anymore. Of course, you will see activity somewhere if you look far enough. So, and this will happen if the density of particles is small. And on the other extreme, if the density of particles is large, then the system, we say it explodes or it doesn't stabilize, which means that this activity will propagate forever. And by monotonicity, we can then push up to which point do we have fixation, and push from the other direction up to which point do we have this activity. And well, they will meet at some parameter. Let's call this parameter zeta C. Zeta stands for density, C stands for critical, and they should match. Right? This is the same coefficient here that we have, this proportionality factor of what is the proportion of the volume of this region here that we were able to retain of particles in the previous version of the dynamics. Let's skip a bit this motivation and physical discussions and describe the activated random walks not within particular choice of parameter of a billion networks, but rather as a continuous time particle system. So what you can see here is a typical configuration of a particle system at a fixed point in time. So I froze time and I look, what is the configuration of my system? Well, there are particles all over the place. And the particles, they come in two colors, red and blue. And this is the configuration. You see, what you see is first, there is no constraint on the number of particles that share the same site. Okay, so these are just what we see here is just 5 particles that are at the same site. There is no relative position between them. It's not that one of them is on the top of the other. This is just a way of drawing it. Here it just says there are 5 particles in this site. Sites can have 0 particles. And if they have a blue particle, it has to be only one. They can only have one blue particle. And what's the dynamics? How does it evolve? So if this is the configuration at time t, and we want to know what's the configuration at time t plus an infinitesimally small amount of time, that means we want to know what are the transition rates. And the transitions are the following. An active particle, which is red, can decay and become blue or sleeping or however we want to describe it. This will occur at some rate lambda. Lambda is just a fixed number. We can think of lambda equal 1 if you want. It's okay. It's just a fixed parameter, which is the decay rate. Let's call this the decay rate or the sleep rate. Well, what else happens in this dynamics as we go from a certain time to a time infinitesimally small after that? Well, active particles, they jump. Jumping means a particle at site X will choose a site, let's say X plus Y, and jump there according to some randomly sampled Y. Okay? So I emphasize X to X plus Y instead of Z to W, because I want to emphasize that, well, I'm assuming that the jump distribution only depends on the size of the jump, meaning this jump, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. The probability of this jump is the same as the probability of this jump. Yeah, so we want this whole thing to be a translation invariant. Yes. And now the final ingredient, because so far these particles are not interacting at all. And so far I have not specified what should happen if this particle jumps here, as we are not allowed to have 2 blue particles and more particles at the same site. What happens is if an active particle and a sleepy particle are at the same site, then immediately the sleepy particle becomes active. So you see particles, they come in 2 colors, but they switch back and forth between colors. Okay? So this is switching color and this is switching color. And it is a conservative particle system. We never lose particles in this dynamics. No, undo. So I think it's a good point to ask if you have questions, because the entire talk is about this model. And if this model is not clear, there's no point in not asking. Yeah, Takis, I think you cannot unmute yourself. Maybe you have to write in the chat.
I can try the.
So is sleepy, it cannot by itself become active. So let's, yes, thank you for the question. Blue particle does not jump. Yeah, blue particles, thank you. So I'm getting all these questions. Yes, let's say, let me add here, S jumps at rate 0. Okay, blue particles, they don't jump. And and blue particles, they don't turn red spontaneously. Yeah, red, they turn blue spontaneously. So this would be some spontaneous decay. They're active and they decay to sleepy, and they're not spontaneously activated. The only way this blue particle here will ever become red is if some other particle comes into that site. The goal of the system is to wake up all lazy bums. What's the initial configuration? I'm not discussing the initial configuration at this point. I'm just discussing the mechanism. How does this system evolve in time given its present configuration? And the system doesn't really have a goal. Yeah, the system, there is no ASS. No, you can never get ASS because you cannot never get SS. If you see, if these are the only transitions you allow, you'll never be able to get an SS. Thank you for all these questions. This has been very helpful. If you have more questions. Yeah, so they are lazy and they try to wake up each other, and if there are many of them, they will manage to. If not. So there's some cohort phenomenon here. Let's not do many social analogies. It's not a good idea. So I'll make the following assumptions. I don't have a good reason to justify them. They're just reasonable enough to be interesting, but strong enough that I can state all the upcoming results without specifying assumption for each of them. So let's assume the jumps are to nearest neighbors, but I don't assume it's a uniform or even symmetric or a biased, unbiased. It can be anything. It can be even deterministic. You always jump to the right, or you always jump north or east in 2 dimensions. All my particles stay active. We can discuss this further later. And this, we'll discuss this more later as well. It's not really important, but we want to have something concrete in mind, and we want to have something where it is obvious that by increasing the density, we can compare configurations. So for the time being, let's say at time 0, I'm going to place an IID. IID means independent from the other sites, a number of particles at each site, and it will be Poisson with a certain parameter zeta. Zeta stands for density, as usual. But we want lambda to be not 0, because 0 will be just a bunch of random walks that are not talking to each other, that are not interacting. You can consider the case of infinity, which was pointed out by Lionel. It corresponds to infinity would be ideally. And well, okay, of course, the first question we want to ask is the fixation versus activity. So these are 2 events. Okay? Once we have our particle system, we have a realization of our particle system. So for each time t, we have eta t. Eta t just gives you a complete description of what the configuration of the system is at time t. I'm not writing explicitly what's the configuration space. It's there are 2 events. These events, they may occur or not. So it's enough to observe what's happening here and determine whether they occur or not. Okay? Fixation is the event that each site is eventually stable. And activity is the event that each site is visited infinitely many times. Well, obviously, these 2 events are mutually exclusive. And it's reasonable that one of the 2 must occur, because some sites being eventually stable and some sites being visited infinitely many times is not reasonable. If you jump to every neighbor with positive probability, then it's obviously not possible. But even if you're jumping just in one direction, it's not possible by making ergodicity considerations. So there is a dichotomy, moreover, which says either one of the 2 will happen with probability 1. Okay, not only one of these 2 must occur. It cannot be that the first one occurs with probability 1/3 and the second one occurs with probability 2/3. And well, that also by ergodicity considerations, you can prove that. And so now let me insist here. Once you fix the graph, and I'm most interested about ZD. So let's say once you fix the dimension D, and you fix the jump distribution. So P for me is a probability distribution on ZD, which just describes how the particles are jumping. So is the chat, nothing in the chat? No. So once we know the dimension and how the particles are jumping, we still have two parameters. So we have a two-dimensional family of models. Yeah, so one parameter is the decay rate. And one parameter is the density. And if we pick each point in this quadrant, that point will specify a model for us once these two are fixed. And what this dichotomy property is saying is each point in this plane, it gets a color, blue or red, depending on which of these two events will occur with probability 1. So on the top of dichotomy, we also have monotonicity. It may not be completely obvious at this point, but let's just believe this, which is the following. If we have a point on the plane, we know the model corresponding to that point, it remains active. Then by increasing the density of particles or decreasing the sleep rate, or both, of course, you still get a model that stays active. Well, assuming this is true, then the converse is also true, which is if you have a model that fixates, then by increasing the sleep rate or by decreasing the density, we get a model that also fixates. So this is what I call here monotonicity. And because of monotonicity, then for free already, we get the existence of a curve that only goes north and east, which separates these two regions. Just like for one parameter models, just by elementary monotonicity considerations, we usually have the definition of a critical parameter just as the supremum of a parameter for whatever this means, or the infimum of the parameter for whatever this means. This gives us existence of a critical parameter, and it may not give us for free the fact that this critical parameter is non-trivial. You know, it could be 0, it could be 1, it could be infinite, depending on what the model is. But it does give existence of a curve. It could, in principle, be like this. It could be like this. It could be quite bad. But this comes from monotonicity. And the conjecture is, well, the curve looks very reasonable. So it doesn't go up like this. It doesn't go to the side like this. It's just a curve that, so let's state precisely what this curve means instead of making descriptions. So first, forget about smoothness or inflection point. So maybe this looks like an inflection point. This is completely out of scale. This is so much out of scale that I managed to put infinity on this graph. Okay, so this is, of course, not on scale. What is being stated here in this picture is that, well, this curve, it is continuous, it is strictly increasing, it's reasonably smooth. And for whatever density below 1, we can take the sleep rate high enough so that the system fixates. For whatever finite sleep rate, we can take the density high enough so that the system stays active, and so on. So if we can always, once we fix the density, we can always pick the a sleep rate so that it fixates, and a sleep rate for which it fixates and stays active. And if we fix the sleep rate, likewise, we can take the small enough density so that it fixates. So the curve looks like this. It does not have horizontal segments. It does not have vertical segments. From 0, 0, it starts right off into the interior of this region. And also from 1, infinity, it also starts right off into the interior of this region. There is one parameter here. There's one number here, 1, which is not universal. This is just a particular feature of this model. What's this number 1 here? Well, 1, if you remember what's the description of this dynamics, 1 is just the maximum number of particles that you can hold on a given site. Yeah, this is the most optimistic amount of mass that you can hold if you will fixate. If your particles will each one of them find a a place to sleep. Well, at the critical density or near the critical density, there should be no fixation, power laws. We should have interesting scaling limits, bursts of activity, etc. This critical density, and this is now indicating universal properties of this model. Unlike most of the other abelian models, the critical density here should not depend on the fact that I said IID Poisson. Moreover, this picture here, which has been defined for the infinite volume, it should have a counterpart for finite volume. Finite volume would be, we take a large torus, large but finite. Once it's finite, it doesn't make any sense. It doesn't make any sense anymore to discuss whether this particle system will fixate or not. It will fixate because it's a finite space. There are only finitely many configurations. It's just a Markov state, Markov chain on a finite space state space. It will fixate. So the question is how much it will take for it to fixate. And the conjecture is away from the critical curve. Away from the critical curve, you're fixating either exponentially slow or polylogarithmically fast. And as I said, this critical curve should be continuous, strictly increasing, etc. Let me skip this part here, these challenges. This is why, let me just say why it is extremely challenging then to study this system is the conservation of particles. Conservation of particles really is playing against us here in the sense that if we try the typical arguments we're used to, block arguments with 2 or 3 steps of renormalization or infinitely many steps or trying comparisons, the problem is because particles are conserved, we can't really go around the problems like we can in percolation or contact process, these types of models where we have some argument and we want to say there is no path from here to here, or there is a path from here to here. We make some blocks, and if we don't see what we want in this block, it's fine. We can just look at the neighboring block and maybe we find it there. And if we find it there, then it doesn't matter the fact that we found a problem before. And when particles are conserved, then it becomes much harder. If you have a problem, you cannot just, let me ignore this region and try to find a solution on a neighboring block, because the problem is still there. You still have to take care of it. And this is if you're trying to prove fixation. If you're trying to prove that the system stays active, well, you want to show active occurs. So these particles, they have to come from somewhere. And once something happens to them, then they're gone. Then you need new particles to work with. And this, in technical terms, this would translate into this statement here, which is a typical approach where you would try some overcounting of all possible ways in which things would go wrong, get a good estimate on the exponential growth of this counting if these are indexed by some parameter, like the size of the event or the number of open edges, etc. And once you have this overcounting, just punish these configurations, all of them simultaneously by choosing one parameter to be extreme. Extreme can be close to 0, close to 1, large enough in different cases. And these just don't seem to work here because of conservation of particles. So let me state some results. First, general results about this model. First, the tools we work with is, well, one based on abelianness. And for mathematicians, if we try to dig the history, didn't dig it until the bottom, there are these 2 papers that cite each other, and they don't quite, if you ask them, they don't tell you which one did it first or whatever. It's these card games of Diaconis and Fulton, which Vladas Sidoravicius and myself imported into the activated random walk context and made a general framework for us to prove that the points in the space are certain model is fixating or active. Then another tool is to have a particle-wise construction where all the randomness, and it doesn't use any abelianness whatsoever, you put all the randomness on the particles, meaning at time 0, each particle is given a life plan, and it just follows that plan, and they interact as they follow the plan, they interact by the fact that if one of them is sleeping and another one comes, then it resumes its life plan. What happens at the curve? Yeah, at the curve is when you get all this interesting critical behavior. The system does not fixate, but it goes to, it takes too long. It doesn't fixate, but it just gets lazier and lazier, and it converges to a critical state in law, even though you still get activity in each given site infinitely many times. So if we have a particle-wise construction, and assuming a particle-wise construction is well-defined, because it's not clear if you try to define from this randomness particles, this eta t, the entire history of the system, assuming that there is this remark by Amir and Guralgrevich, which says, if a particle, so we label the particles, they are distinguishable mathematically, not physically. If we label the particles and we say that a particle has positive probability of staying active, their remark is that sites also stay active. So they basically rule out the case where particles stay active, but they drift away to infinity in a way that sites still fixate. The inverse of this implication is rather obvious. If a particle fixates, so this will be the inverse implication, then of course sites fixate. Why? Well, because in order for the particle to fixate, it has to fixate in some site. So they proved this, and this turns out to be very useful. And then many years later, Laurent Tournier and myself, we found an argument that was using this tool by Amir and Guralgrevich, and we got an averaged criterion that makes it a bit easier to prove activity. And in order to use this, then we prove that this construction is indeed well-defined, and well-defined in a way that is translation invariant function or translation covariant function of the randomness, which allows us to use properties such as ergodicity, mass transport, resampling, couplings of different types. And basically, we went to the typical criterion for activity, which is that typically we have to prove to show that the system stays active. There's the odometer function defined by Lionel. We want to show that the odometer function is very large with positive probability. That's how you do it typically, but this is quite restrictive because in order to show something occurs with probability bounded from below, one way would be to say, well, the expectation is high and the variance is not that high. So you need to control the variance. That means more work and more restrictive results. And this alternative criterion is we just need to look at a very large box, let this box stabilize, and see if a positive fraction of the particles have to leave the box on average. And on average is much easier to handle, just adding probabilities when you compute this expectation. So about the sharpness of the phase transition towards this, all this discussion of universality that you have been following so far. So once we fix the dimension and the jump distribution, now we have this two parameter family of models. Let's fix also the density or the sleep rate. So if we are here on zeta lambda, let's also fix lambda. So now we just have a one-dimensional family of models. So this theorem is a joint work with Vladas Sidoravicius and Olivier Zindi. It says, forget about IID Poisson. There exists one number, and this number will divide every possible translation ergodic with respect to the group of translations of the graph. That every ergodic translation, it can be classified just according to the average number of particles. If the average number of particles is larger than zeta c, the system will stay active almost surely. If it's smaller, the system will fixate almost surely. There is a shortcoming of this result. Oh, again, no. There is a shortcoming of this result, which is we have to assume, and the proof really relies on it, that all particles start active. And this should not be necessary. It is enough that just a positive fraction of the particles stays active in order to have activity, and we are unable to prove that. So this assumption is relevant here, of course. Here, if you allow some particles to start sleeping, or you're pretty happy, you're fixating even more. For continuity of a critical density, there is a recent preprint by Lorenzo Taggi that says this function here, well, if I draw it this way, the function is strictly increasing. So it says that this function cannot have yes. Like Lorenzo is in the audience, he can correct me. So the critical curve cannot have horizontal segments. So this is what's ruled out by the theorem. Okay, so this if lambda c of zeta is strictly increasing. Or if you want to write as zeta c as a function of lambda, so now this is in the independent variable, and zeta c is the dependent variable. So it's continuous. It's continuous away from 0 and away from infinity. Another result, which is there's a first-hand news. It's not published anywhere. There's no preprint about this. Lionel Levine was kind enough to send me a working draft of this joint work with Vittoria. And I haven't understood entirely the arguments. They didn't quite have the time, actually. But I'm just rephrasing here the way they state one of the results that I'm quoting here. They don't state it that way, but I find it much nicer this way. And it's the following. It's the same as IDLA, but now we've activated random walk as the relaxation mechanism. We start with a bunch of particles, let's say n particles at a given site, 0. So this is the initial configuration. And we just let the dynamics run here until it's over. It will be over, of course. We just have finitely many particles. At some point, you have sleeping particles here and there. This is what we'll have in the end. And if we call the length of this interval, the interval consisting of all the sites that have been visited in this process, this is symmetric, 1/2, the jumps. So this is a simple random. Is that true, Vittoria? This is for a symmetric random walk, like Vittoria, 1/2. So if you call this L, and you define n, divide n by L, so what you have, let me call it here in quotation marks, is the density of this final configuration. So the theorem says this density, it stays bounded from above and from below by 2 constants, but it's not just that exist 2 constants. You can define these constants very explicitly, and they should both be equal to the zeta, the critical density. This one, which I call SOC, that's how physicists will call it, the dynamics, is the one that we get if we take a box, add an enormous amount of particles to this box. It doesn't matter how you do it, because the way activated random walks spreads mass. You let it stabilize by killing whatever particle leaves the interval. You measure that density. And if with high probability, you must have at least some zeta, and you take the smallest such zeta. This is the zeta called SOC. So it's basically how much particles you keep here asymptotically, of course, as the size of this interval here becomes larger. And zeta fast, here fast means, let me clean the board a little bit. Zeta fast is the largest density that we have, such that when we stabilize the infinite system, and we measure how many times each site was visited. Okay? That's called odometer for historical reasons, but then we stick to that nomenclature. So you stabilize a configuration that started with parameter zeta, and we count how many times a site is visited. If that variable is not only finite, finite you would get exactly zeta c. But you ask a little more, you ask that it has a third moment, I think. And you take the highest possible density with this property, call that zeta fast. conjecturally, these two should be the same. However, we still need to prove that this one is positive at least. Okay, next result. Let me now go very quickly, since this is recorded, about the phase diagram. Let's focus here on what this is. This is the plane for the two-dimensional family of models. Now, what model I'm talking about? I'm talking about, in dimension 1, a very degenerate version of the activated random walks. It is particles, they jump to the right with probability 1, they jump to the left with probability 0. So this is an extreme case, but once this is fixed, we have a model and with two parameters, density and sleep rate. But now let me have now 6 families of models depending on dimension, whether the walks are biased or unbiased, simply because all the arguments and the papers and that are currently known will work for different cases. So this is what we had 13 years ago or 14 years ago, just a white canvas. And our job is to add paint to it, is to say, oh, this, let's prove that this stays active, let's prove that this fixates, and so on. So let me just flash a little movie for you very quickly. So there was some works where this was proved little by little. So first, for the simplest case, dimension 1 directed walks. Then it keeps going, like still in 1 dimension, no results in higher dimension, and it keeps going. So we study here some the scaling limit of the model here, and we kept, so we started adding ink to this diagram. Here's when we consider finite system and prove that it's fast here and slow here, and so on. And finally, this is what we know currently. And of course, the most disturbing part of this history of this story is that we don't have any red here. We don't have any red here. We don't even have any red here, which is an open problem. And so far, no clue on how to tackle it. Some other results about scaling limits and avalanches. So let's consider 1-dimensional model. Particles only jump to the right because that's the kind of exactly solvable case or integrable case in some sense. And I'm going to define some ad hoc dynamics, which is the following. For each number n, I will look at an interval of length n. I will stabilize that interval. Once you stabilize, you get blue particles inside and a few particles who manage to escape. We'll call Cn the number of particles that manage to escape. So this gives us a random variable taking value on natural numbers. That the definition should be very clear for fixed n. But now I want to insist what is the joint distribution for every n. So how do we go from n to n plus 1? Well, I'm going to release these 2 particles here, but they will interact with the leftovers of the step n. So they have a chance to activate these particles and they help each other so that we get Cn to increase. And I'm fixing some IID configuration. Now it does matter because I'm not on an infinite space and discussing that type of problem anymore. And I'm fixating even that the density should be exactly equal to the critical density, which we know exactly only for this model. It's a 1-dimensional directed model, or directed models in general. And so if we do this, so this was n equals 0, n equal 1, n equal 2, and I'm going to increase to n equals 3, which means I'm just about to release these 2 particles and see what happens to them. Okay, here they sleep. I increase n again, so now I'm just about to release this particle. And you see that releasing this particle caused, well, some activity here, and this particle ended up here, this particle ended up here. So this is how it is defined. And so for each n, we have a value of Cn. You see that typically Cn does not increase. And it turns out when it increases, it increases by quite a lot. And we call that an avalanche. So here's a point where it increases. And there's this macroscopic gap here that particle. So this is really a function from natural numbers to natural numbers. And well, this is a theorem by Manuel Cabezas and myself. It is on the archive, and it's to appear in this volume in memory of Vladas. Now it says if we rescale this counting process, it converges to a process which is completely discrete. It just has constant pieces and jumps. And of course, because this process is self-similar, it must have jumps accumulating, but they only accumulate at 0. So they really look like that simulation. And there is one parameter here, which is not just scaling. Let me show you simulations of many different values of this parameter. So this parameter depends on the variance of the initial configuration. And it is non-Markovian, and of course it's non-Markovian. No, not of it, and it looks like this. Let us mention some proofs. So general framework of a toppling procedure, because of the abelian property, which, as Lionel said, it is you can play God and you can decide on which order you will update your configuration. When you do that, you can define the odometer. So MV of X is, you have a random configuration eta. You have this random stack of instructions that tell how to perform, how to update the system once you want to update the system at a given site X. These two random objects are fixed. Now, what is MV of X? It just counts how many times we have to update site X when we stabilize the configuration inside V. And it turns out this random variable, as we let V increase, this will increase to another random variable, which is either infinite with probability 1 or finite with probability 1. And therefore, we have a very convenient characterization of when you are in the active phase or in the fixating phase. So these are examples of estimates on the critical parameters that are all done following this framework of specifying a toppling procedure. And let me now describe in more detail one case, which is the only case known where we have been able to prove that a system stays active without the underlying random walk being transient. And this is a breakthrough work by Riddhi Prasim Basu, Shishendu Ganguly, and Chris Hoffman. And the theorem would be in dimension 1, the random walks being simple, symmetric random walks, half probability of jumping to the right, half probability of jumping to the left. Let me state it this way. For any value of the density, the critical sleep rate is positive. Of course, you can always rephrase it by saying for small enough lambda, the critical density is less than 1. And not only that, it tends to 0 as lambda tends to 0. And the idea of their construction is, of their argument is the following. You just need to specify one legal way to topple the configurations. Of course, this will be random because the outcome of each time that you update your configuration, the outcome is random. So your procedure, it should react to that randomness. It should respond to the randomness. And the procedure they introduce in order to obtain independence and use the fact that we can take this lambda as small as we want, but still have independence and get rid of all dependencies. The idea was, let's do blocks. Let's say this is a block of particles, and I want to show that when we stabilize this configuration, many particles will have exited through the boundary. This is the goal. And in order to get there, well, we just split this region into departments. And if we're not going to have too many particles, a large number of particles exiting this interval, it means we have retained many particles inside. And we're just going to, well, organize this in a business manner, which means we have these departments. And if you're going to retain many particles inside, well, someone is guilty for it. And what we want is just that each department does not want to be guilty. Each department just wants to do its job. And its job is, well, every particle that arrives to the center of this department, we're going to handle it properly, and we're going to send it to one of the neighboring departments, and it's no longer our problem. This is how the approach works. But now we want these departments to be independent so that they cannot blame each other for any failure. How do we introduce independence? Well, we artificially assign a color to the particles, and I'm picking these two ugly colors, purple and yellow, to be clear that it has nothing to do with the dynamics. We artificially color the particles yellow and purple, and we declare, let me ignore interaction between particles of different colors. This is what will introduce independence across different departments, or about how well each different departments are doing their job. And so this is a purple department, which means it's responsible for what is happening to all these purple particles here. And its goal is to make sure they all leave. I don't want particles in my department. That's the goal. That's the game we're playing here. And in order to get independence, I'm going to allow this, okay, which is this particle was sleeping, but it is being controlled by the yellow department. And after that, some purple particle came here, but all these yellow and purple is completely artificial. It's not in the dynamics of the model. This purple particle comes here, and I'm going to say, I'm still going to pretend this yellow particle is sleeping. I don't want any interaction between these departments, except the fact that departments are sending particles and they are arriving at the center of the other department. Okay, so this block here, it has a particle which is sleeping, and this block here is sending a purple particle. Maybe it will arrive here, maybe it will arrive here, but we don't want any help from it. So the yellow department doesn't want help from it. We want to keep independence when we do our estimates later on. And then when you want to show that to have a low number of particles exiting here, what we do is we count, well, how many particles can we emit from this department here? In how many ways can we emit particles here that give exactly that number? And what they do is they consider this tree of possibilities. You fix how many particles you want to exit through the left, and then there will be this random collection of how many particles you're going to emit from the center of the other department that are consistent with getting that number coming out there. And now for each of these numbers, we look at how many number of particles can we emit from the center of the next department that are consistent with sending the right required number of particles to the previous block, etc. And I rephrased their approach, but I really didn't add anything new there. I just made it more abelian or more clear that this is something that was for me more amenable to study, which is I split this line here, this chain of sites into two. So now this site will be yellow. This one will be the purple. This purple. Yes, I'm sorry, I don't have yellow. This yellow and yellow, and to make it clear that they don't interact, I even split the sites that they occupy. And I add this site here that I call it just buffer. Nothing's happening at this site. Whatever enters this site has to go to the next block. This buffer is just to do bookkeeping. It's just to measure how many particles are changing color from the neighboring departments into your department. And so we want to analyze these buffers. And what you can do now is look at a single block and do all your analysis on a single block. You're receiving particles from the middle, and you don't care why you receive those particles. You just have this M, so how many particles you receive. And for each value of M, you can plug it here, and you have these random functions which say, how many particles do you emit to the left, how many do you emit to the right, and how many do you have sleeping in your block if you add M particles to the middle and stabilize. And by abelianness, it doesn't matter if you add them all here at once and stabilize, or if you stabilize first and then increase M a little bit, stabilize again, increase M a little bit, and stabilize again. And since we have no idea what these vector MIs are, these MIs are the odometer at the buffers, and how to approach them, well, we write this mass balance equation, which just says the number of particles that arrive at a given site is equal, the number of particles we have to emit to the left equals the number of particles that the block on the left is expecting minus the number of particles that that block has already received from the right. And we use this constraint to bound our sum. And in the end, what we want to make them bound exponential moments. And to disentangle these moments, instead of now looking at this mass balance equation as a restriction, what we do is, well, take the supremum over all possible numbers of particles that this block to your left can be expecting from you, and estimate just the contribution of that block to this exponential moment. And then you multiply, and everything will follow from that. From this approach, we joint work with Amin Aslai and Bruno Chapirat. We have proved that not only lambda critical of zeta is positive, we show that there are constants from above and from below that we can bound. So the critical density is bounded from above and from below by multiples of the square root of lambda, well, consistent with the diffusive nature of this model. And recently, with Chris Hoffman and Jacob Ritchie, we've now considered the case where the sleep rate is high, and then we don't have the luxury to split particles into groups anymore, because we want to have the density very close to 1, so we cannot do that splitting anymore. So what we do is split particles into 2 types, and we have most particles are just they are carpet particles, and even most of them will be carpet particles forever because they are here, which just means there are safe regions where my non-carpet particles or free particles will be able to travel on top of them. And we have these little holes, which are the ones that pose all the difficulty. We must have little holes because we're trying to prove that the critical density is less than 1. So we must allow for these little holes with some positive density. And now the whole work is to make an analysis of what happens in a given block, but now having this little hole, it's sometimes here, sometimes there, because once a free particle arrives there, once a free particle arrives at the hole, and we want this particle to continue moving, well, typically it will fall asleep. And when it falls asleep, we have to declare it now carpet and trade it for a particle which is not sleeping. And so there's this whole business of controlling where this hole is going, and saying this hole will stay close to the center, so that this business can be done safely and without trouble. Let me quickly mention some open problems. So of course, there's this show that the critical density is less than 1 in 2 dimensions. Show that in the 1-dimensional torus, not only you have a region with a slow fixation and a region with fast fixation, it's good to show that there's nothing in between, which doesn't come from free, just from elementary considerations. Show sharpness of this phase transition without assuming that all particles start active, and give alternative proofs of fixation and activity in some cases, not relying so much on ergodic theory and on infinite dimensional, infinite volume type of tricks. These are references. If you're interested in studying this further, I'm only quoting the references that are not included in this recent survey that I have written. But you see, this is quite active. After I wrote the survey, there's already 5 papers. When there's a little more, someone else will have to write a new survey about it. And that's all. Before I'm over time, let me just thank you for staying here so far.
Okay. Thank you, Leonardo, for your nice talk. So now I'm going to allow everyone to unmute themselves so we can thank all together Leonardo for a nice talk. So now you should be able to unmute yourself. And now, well, you can ask if you want to. You can unmute yourself and make any questions you may want to ask Leonardo.
So I have a question. So I'm Alessandra
Yes.
Fagionato. Yes, but so what about the long jumps? Are there at least simulations, conjectures? So if the random walk can perform long jumps.
Unmute. Thank you, Bernardo. So for long jumps, most of the results I stated, except those in one dimension, they actually don't care about the jump being a nearest neighbor. It's really in one dimension that we know fundamental theorem of calculus. If you go from point A to point B, you visit every point in between. And this is used in almost every argument in one dimension. Other than that, I mean, mathematically speaking, the results don't really care about what is the jump distribution. It can have heavy tail, it doesn't matter. It just needs to be diagonally translation invariant, if that makes sense. I mean, the probability of jumping from here to here is the same as the probability of jumping from here to here. I mean,
So another question, if you, so you ever talked about CD? You have always
Yes.
worked with the CD. What about other graphs?
Many of the results they hold in other graphs, Cayley graphs or trees or graphs with enough many symmetries. So the abelian property, you don't even have need any symmetry. The abelian property, you don't need anything. Conservation of mass and certain other arguments, they certainly depend on the graph being unimodular. Unimodular, not the graph itself. Unimodular with respect to at least some, with respect to some group of automorphisms, which is under which your jump distribution is invariant. Transitive group of automorphisms. So let's bring this down to Earth. That means on Z2, just translate, you don't need symmetries like reflection symmetries, just translation invariance is enough, because if you just consider the group of translations, this is a transitive group of automorphisms of Z2, and it is unimodular. So it's enough that the jumps are translation invariant on Z2. Yeah, you don't need the random walks to respect all the symmetries of the graph. You can just ignore many of them.
Okay, so are any other questions? So I wrote some questions. Let me see. Okay, I had a question about a shape theorem, but it seems that this is exactly the work in progress by Lionel and Vittoria, right?
Yes, looks like it. Yeah, this is one of, and it seems they are very advanced into it. So at least for one dimension. So yeah.
And another question. So this is a little bit related with what Lionel was saying. So it's so activated random walks somehow interpolate between DLA and simple random walks, right? And in the active phase, they look like random, like the usual random walk somehow, and in the fixation phase, they look more like DLA, right? And so the question is, the two things. So first, is that picture correct? And second, then something different happens at the critical line?
I don't quite get the analogy that what they look like in the subcritical and supercritical phases. And
I mean, in a sense, for example, no, so just to give you an example, in the active phase, you imagine that what happens is that, okay, you need some density of particles to maintain your system active, and all the excess density just look like independent random walks. If you look at fluctuations or the different observables that you want to take, they basically look like
Yes, yes. Okay.
And well, in the fixation phase, one should imagine something analogous in some sense. No, for example, the shape theorem. I mean, it's,
No, you can think of what would be the hydrodynamic limit of it. And if you forget the terminology of stable and unstable, there's a very unfortunate crossover of terminology here. That if you think above the critical density, you have configurations which are stable just because everyone's sleeping. But that's not a stable equilibrium, because just by adding a couple of particles, you can destroy it.
Yeah.
And below the critical density, you have only one equilibrium, which is, okay, in terms of, yes, the particles can be spread in many different ways, but you just have everyone's sleeping. So you can think of a PDE, which is basically whenever you are below the critical density, nothing's happening, and whenever you're above the critical density, the flux of particles would be the gradient of this function that tells you, well, what's the proportion of active particles for that total density of particles. And your PDE would be UT equals minus the divergent of the flow. I know you are very much into this type of physical description, but yeah, I don't know how to go any further in the metaphor that you're proposing.
Okay. And then in the critical line, it's something different, no?
Yeah, on the critical line, what you have is a system that is getting slower and slower. It's never, the activity is never ending, but it's getting slower and slower as a power law. And it's spreading the mass. Yeah, you have many interesting phenomena there. You have hyper-uniformicity, which means that the configuration you see after a long time, it has lots of cancellations in the fluctuations. So the variance of how many particles you see in a given interval doesn't grow linearly with the size of the interval. That's how that's the mathematical formulation of hyper-uniformicity. It means mass is spread much more evenly than if it was random.
Okay. Well, if there are not further questions, let's thank both of the speakers of today, Leonardo and Maria-Lionel, for their very wonderful talks. Okay. And final remark, just okay. So maybe we will send an email. So in some places in the world, time is changing next week. In other places, it's not changing. So just to warn you to stay tuned to these changes, so you don't miss next week seminar.
That it stays at the same time UTC, right? It's not
Right.
dragged by Europe or anything like that.
No, in principle, yes. No.